evaluating foundation models. Because evaluation is difficult, many people settle for word of mouth too, e.g., someone says that the model X is good, or eyeballing the results. 3. This creates even more risk and slows application iteration. Instead, we need to invest in systematic evaluation to make the results more reliable. Since many foundation models have a language model component, this chapter will provide a quick overview of the metrics used to evaluate language models, including cross-entropy and perplexity. These metrics are essential for guiding the training and fine-tuning of language models and are frequently used in many evaluation methods. Evaluating foundation models is especially challenging because they are open-ended, and I'll cover best practices for how to tackle these. Using human evaluators remains a necessary option for many applications. However, given how slow and expensive human annotations can be, the goal is to automate the process. This book focuses on automatic evaluation, which includes both exact and subjective evaluation. The rising star of subjective evaluation is AI as a judge, the approach of using AI to evaluate AI responses. It's subjective because the score depends on what model and prompt the AI judge uses. While this approach is gaining rapid traction in the industry, it also invites intense opposition from those who believe that AI isn't trustworthy enough for this important task. I'm especially excited to go deeper into this discussion, and I hope you will be, too. Challenges of evaluating foundation models. Evaluating ML models has always been difficult. With the introduction of foundation models, evaluation has become even more so. There are multiple reasons why evaluating foundation models is more challenging than evaluating traditional ML models. First, the more intelligent AI models become, the harder it is to evaluate them. Most people can tell if a first grader's math solution is wrong. Few can do the same for a PhD-level math solution. For it's easy to tell if a book summary is bad if it's gibberish, but a lot harder if the summary is coherent. To validate the quality of a summary, you might need to read the book first. This brings us to a corollary. Evaluation can be so 114, Chapter 3, Evaluation Methodology. Much more time-consuming for sophisticated tasks. You can no longer evaluate a response based on how it sounds. You'll also need to fact-check, reason, and even incorporate domain expertise. Second, the open-ended nature of foundation models undermines the traditional approach of evaluating a model against ground truths. With traditional ML, most tasks are close-ended. For example, a classification model can only output among the expected categories. To evaluate a classification model, you can evaluate its outputs against the expected outputs. If the expected output is category X but the model's output is category Y, the model is wrong. However, for an open-ended task, for a given input, there are so many possible correct responses. It's impossible to curate a comprehensive list of correct outputs to compare against. Third, most foundation models are treated as black boxes either because model providers choose not to expose models' details, or because application developers lack the expertise to understand them. Details such as the model architecture, training data, and the training process can reveal a lot about a model's strengths and weaknesses. Without those details, you can evaluate only a model by observing its outputs. At the same time, publicly available evaluation benchmarks have proven to be inadequate for evaluating foundation models. Ideally, evaluation benchmarks should capture the full range of model capabilities. As AI progresses, benchmarks need to evolve to catch up. A benchmark becomes saturated for a model once the model achieves the perfect score. With foundation models, benchmarks are becoming saturated fast. The benchmark GLUE, General Language Understanding Evaluation, came out in 2018 and became saturated in just a year, necessitating the introduction of Super GLUE in 2019. Similarly, Natural Instructions, 2021, was replaced by Supernatural Instructions, 2022. MMLU, 2020, a strong benchmark that many early foundation models relied on, was largely replaced by MMLU Pro, 2024. Last but not least, the scope of evaluation has expanded for general-purpose models. With task-specific models, evaluation involves measuring a model's performance on its trained task. However, with general-purpose models, evaluation is not only about assessing a model's performance on known tasks but also about discovering new tasks that the model can do, and these might include tasks that extend beyond human capabilities. Evaluation takes on the added responsibility of exploring the potential and limitations of AI. Challenges of evaluating foundation models 115. 5. I searched for all repositories with at least 500 stars using the keywords LLM, GPT, generative, and transformer. I also crowdsourced for missing repositories through my website https://winchip.com. The good news is that the new challenges of evaluation have prompted many new methods and benchmarks. Figure 3.1 shows that the number of published papers on LLM evaluation grew exponentially every month in the first half of 2023, from 2 papers a month to almost 35 papers a month. Figure 3.1. The trend of LLM's evaluation papers over time. Image from Chung et al. 2023. In my own analysis of the top 1,000 AI-related repositories on GitHub, as ranked by the number of stars, I found over 50 repositories dedicated to evaluation, as of May 2024. 5. When plotting the number of evaluation repositories by their creation date, the growth curve looks exponential, as shown in Figure 3.2. The bad news is that despite the increased interest in evaluation, it lags behind in terms of interest in the rest of the AI engineering pipeline. Balduzzi et al. From DeepMind noted in their paper that developing evaluations has received little systematic attention compared to developing algorithms. According to the paper, experiment results are almost exclusively used to improve algorithms and are rarely used to improve evaluation. Recognizing the lack of investments in evaluation, Anthropic called on policymakers to increase government funding and grants both for developing new evaluation methodologies and analyzing the robustness of existing evaluations. 116, Chapter 3, Evaluation Methodology. Figure 3.2. Number of open-source evaluation repositories among the 1,000 most popular AI repositories on GitHub. To further demonstrate how the investment in evaluation lags behind other areas in the AI space, the number of tools for evaluation is small compared to the number of tools for modeling and training and AI orchestration, as shown in Figure 3.3. Inadequate investment leads to inadequate infrastructure, making it hard for people to carry out systematic evaluations. When asked how they are evaluating their AI applications, many people told me that they just eyeballed the results. Many have a small set of go-to prompts that they use to evaluate models. The process of curating these prompts is ad hoc, usually based on the curator's personal experience instead of based on the application's needs. You might be able to get away with this ad hoc approach when getting a project off the ground, but it won't be sufficient for application iteration. This book focuses on a systematic approach to evaluation. Challenges of evaluating foundation models 117. 6. While there's a strong correlation, language modeling performance doesn't fully explain downstream performance. This is an active area of research. Figure 3.3. According to data sourced from my list of the 1,000 most popular AI repositories on GitHub, evaluation lags behind other aspects of AI engineering in terms of open-source tools. Understanding language modeling metrics. Foundation models evolved out of language models. Many foundation models still have language models as their main components. For these models, the performance of the language model component tends to be well correlated to the foundation model's performance on downstream applications. Liu et al., 2023. Therefore, a rough understanding of language modeling metrics can be quite helpful in understanding downstream performance. 6. As discussed in Chapter 1, language modeling has been around for decades, popularized by Claude Shannon in his 1951 paper Prediction and Entropy of Printed English. The metrics used to guide the development of language models haven't changed much since then. Most autoregressive language models are trained using cross-entropy or its relative, perplexity. When reading papers and model reports, you might also come across bits per character, BPC, and bits per byte, BPB, both are variations of cross-entropy. 118, Chapter 3, Evaluation Methodology. 7. As discussed in Chapter 1, a token can be a character, a word, or part of a word. When Claude Shannon introduced entropy in 1951, the tokens he worked with were characters. Here's entropy in his own words. The entropy is a statistical parameter which measures, in a certain sense, how much information is produced on the average for each letter of a text in the language. If the language is translated into binary digits, 0 or 1, in the most efficient way, the entropy is the average number of binary digits required per letter of the original language. All four metrics, cross-entropy, perplexity, BPC, and BPB, are closely related. If you know the value of one, you can compute the other three, given the necessary information. While I refer to them as language modeling metrics, they can be used for any model that generates sequences of tokens, including non-text tokens. Recall that a language model encodes statistical information, how likely a token is to appear in a given context, about languages. Statistically, given the context I like drinking __, the next word is more likely to be tea than charcoal. The more statistical information that a model can capture, the better it is at predicting the next token. In ML lingo, a language model learns the distribution of its training data. The better this model learns, the better it is at predicting what comes next in the training data, and the lower its training cross-entropy. As with any ML model, you care about its performance not just on the training data but also on your production data. In general, the closer your data is to a model's training data, the better the model can perform on your data. Compared to the rest of the book, this section is math-heavy. If you find it confusing, feel free to skip the math part and focus on the discussion of how to interpret these metrics. Even if you're not training or fine-tuning language models, understanding these metrics can help with evaluating which models to use for your application. These metrics can occasionally be used for certain evaluation and data deduplication techniques, as discussed throughout this book. Entropy measures how much information, on average, a token carries. The higher the entropy, the more information each token carries, and the more bits are needed to represent a token. 7. Let's use a simple example to illustrate this. Imagine you want to create a language to describe positions within a square, as shown in Figure 3.4. If your language has only two tokens, shown as A in Figure 3.4, each token can tell you whether the position is upper or lower. Since there are only two tokens, one bit is sufficient to represent them. The entropy of this language is, therefore, 1. Understanding language modeling metrics 119. Figure 3.4. Two languages describe positions within a square. Compared to the lawn gauge on the left, A, the tokens on the right, B, carry more information, but they need more bits to represent them. If your language has four tokens, shown as B in Figure 3.4, each token can give you a more specific position, upper left, upper right, lower left, or lower right. However, since there are now four tokens, you need 2 bits to represent them. The entropy of this language is 2. This language has higher entropy, since each token carries more information, but each token requires more bits to represent. Intuitively, entropy measures how difficult it is to predict what comes next in a lawn gauge. The lower a language's entropy, the less information a token of a language carries, the more predictable that language. In our previous example, the language with only 2 tokens is easier to predict than the language with 4. You have to predict among only 2 possible tokens compared to 4. This is similar to how, if you can perfectly predict what I will say next, what I say carries no new information. Cross-entropy. When you train a language model on a dataset, your goal is to get the model to learn the distribution of this training data. In other words, your goal is to get the model to predict what comes next in the training data. A language model's cross-entropy on a dataset measures how difficult it is for the language model to predict what comes next in this dataset. A model's cross-entropy on the training data depends on 2 qualities. 1. The training data's predictability, measured by the training data's entropy. 2. How the distribution captured by the language model diverges from the true distribution of the training data. Entropy and cross-entropy share the same mathematical notation, H. Let P be the true distribution of the training data, and Q be the distribution learned by the long gauge model. Accordingly, the following is true: the training data's entropy is, therefore, H, P. The divergence of Q with respect to P can be measured using the Kullback-Leibler, KL, divergence, which is mathematically represented as dKL, P, Q. 120 Chapter 3, Evaluation Methodology. The model's cross-entropy with respect to the training data is therefore, H, P, Q, equals H, P, plus dKL, P, Q. Cross-entropy isn't symmetric. The cross-entropy of Q with respect to P, H, P, Q, is different from the cross-entropy of P with respect to Q, H, Q, P. A language model is trained to minimize its cross-entropy with respect to the training data. If the language model learns perfectly from its training data, the model's cross-entropy will be exactly the same as the entropy of the training data. The KL divergence of Q with respect to P will then be zero. You can think of a model's cross-entropy as its approximation of the entropy of its training data. Bits per character and bits per byte. 1 unit of entropy and cross-entropy is bits. If the cross-entropy of a language model is 6 bits, this language model needs 6 bits to represent each token. Since different models have different tokenization methods, for example, one model uses words as tokens and another uses characters as tokens, the number of bits per token isn't comparable across models. Some use the number of bits per character, BPC, instead. If the number of bits per token is 6 and on average, each token consists of 2 characters, the BPC is 6 divided by 2 is equal to 3. One complication with BPC arises from different character encoding schemes. For example, with ASCII, each character is encoded using 7 bits, but with UTF-8, a char actor can be encoded using anywhere between 8 and 32 bits. A more standardized metric would be bits per byte, BPB, the number of bits a language model needs to represent 1 byte of the original training data. If the BPC is 3 and each character is 7 bits, or 7/8 of a byte, then the BPB is 3/7/8 equals 3. 43. Cross-entropy tells us how efficient a language model will be at compressing text. If the BPB of a language model is 3.43, meaning it can represent each original byte, 8 bits, using 3.43 bits, this language model can compress the original training text to less than half the text's original size. Perplexity is the exponential of entropy and cross-entropy. Perplexity is often shortened to PPL. Given a dataset with the true distribution P, its perplexity is defined as PPL, P equals 2H, P, Understanding Language Modeling Metrics 121. 8. One reason many people might prefer natural log over log base 2 is because natural log has certain properties that makes its math easier. For example, the derivative of natural log ln, x, is 1/x. The perplexity of a language model, with the learned distribution Q, on this dataset is defined as PPL, P, Q equals 2H, P, Q. If cross-entropy measures how difficult it is for a model to predict the next token, perplexity measures the amount of uncertainty it has when predicting the next token. Higher uncertainty means there are more possible options for the next token. Consider a language model trained to encode the 4 position tokens, as in figure 3.4b, perfectly. The cross-entropy of this language model is 2 bits. If this language model tries to predict a position in the square, it has to choose among 2 is equal to 4 possible options. Thus, this language model has a perplexity of 4. So far, I've been using bit as the unit for entropy and cross-entropy. Each bit can represent 2 unique values, hence the base of 2 in the preceding perplexity equation. Popular ML frameworks, including TensorFlow and PyTorch, use NAT, natural log, as the unit for entropy and cross-entropy. NAT uses the base of E, the base of natural logarithm. 8. If you use NAT as the unit, perplexity is the exponential of E, PPL, P, Q equals EH, P, Q. Due to the confusion around bit and NAT, many people report perplexity, instead of cross-entropy, when reporting their language model's performance. Perplexity interpretation and use cases as discussed, cross-entropy, perplexity, BPC, and BPB are variations of language models' predictive accuracy measurements. The more accurately a model can predict a text, the lower these metrics are. In this book, I'll use perplexity as the default language modeling metric. Remember that the more uncertainty the model has in predicting what comes next in a given dataset, the higher the perplexity. What's considered a good value for perplexity depends on the data itself and how exactly perplexity is computed, such as how many previous tokens a model has access to. Here are some general rules. 122, Chapter 3, Evaluation Methodology. More structured data gives lower expected perplexity. More structured data is more predictable. For example, HTML code is more predictable than everyday text. If you see an opening HTML tag like head, you can predict that there should be a closing tag, /head, nearby. Therefore, the expected perplexity of a model on HTML code should be lower than the expected perplexity of a model on everyday text. The bigger the vocabulary, the higher the perplexity. Intuitively, the more possible tokens there are, the harder it is for the model to predict the next token. For example, a model's perplexity on a children's book will likely be lower than the same model's perplexity on War and Peace. For the same dataset, say in English, character-based perplexity, predicting the next character, will be lower than word-based perplexity, predicting the next word, because the number of possible characters is smaller than the number of possible words. The longer the context length, the lower the perplexity. The more context a model has, the less uncertainty it will have in predicting the next token. In 1951, Claude Shannon evaluated his model's cross-entropy by using it to predict the next token conditioned on up to 10 previous tokens. As of this writing, a model's perplexity can typically be computed and conditioned on between 500 and 10,000 previous tokens, and possibly more, upper bounded by the model's maximum context length. For reference, it's not uncommon to see perplexity values as low as 3 or even lower. If all tokens in a hypothetical language have an equal chance of happening, a perplexity of 3 means that this model has a 1 in 3 chance of predicting the next token correctly. Given that a model's vocabulary is in the order of 10,000s and 100,000s, these odds are incredible. Other than guiding the training of language models, perplexity is useful in many parts of an AI engineering workflow. First, perplexity is a good proxy for a model's capabilities. If a model's bad at predicting the next token, its performance on downstream tasks will also likely be bad. OpenAI's GPT-2 report shows that larger models, which are also more powerful models, consistently give lower perplexity on a range of datasets, as shown in Table 3.1. Sadly, following the trend of companies being increasingly more secretive about their models, many have stopped reporting their models' perplexity. Understanding language modeling metrics. 123. 9. If you're unsure what SFT, supervised fine-tuning, and RLHF, reinforcement learning from human feedback, mean, revisit Chapter 2. 10. Quantization is discussed in Chapter 7. Table 3.1. Larger GPT-2 models consistently give lower perplexity on different datasets. Source, OpenAI, 2018. Lombada, PPL, Lombada, ACC, CBTCN, ACC, CBTNE, ACC, Wikitext 2, PPL, PTB, PPL, and Wiki 8, BPB, Text 8, BPC, Wikitext 103, PBL, IBW, PPL, SOTA 99. 859. 2385. 782. 339. 1446. 540. 991. 0818. 321. 8117 M35. 1345. 9987. 6583. 429. 4165. 851. 161. 1737. 5075. 2345 M15. 6055. 4892. 3587. 122. 7647. 331. 011. 0626. 3755. 72762 M10. 8760. 1293. 4588. 019. 9340. 310. 971. 0222. 0544. 575, 1542 Mobile 8. 6363. 2493. 3089. 0518. 3435. 760. 930. 9817. 4842. 16. Perplexity might not be a great proxy to evaluate models that have been post-trained using techniques like SFT and RLHF. 9. Post-training is about teaching models how to complete tasks. As a model gets better at completing tasks, it might get worse at predict ing the next tokens. A language model's perplexity typically increa SES after post-training. Some people say that post-training collapses entropy. Similarly, quantization, a technique that reduces a model's numerical precision and, with it, its memory footprint, can also change a model's perplexity in unexpected ways. 10. Recall that the perplexity of a model with respect to a text measures how difficult it is for this model to predict this text. For a given model, perplexity is the lowest for texts that the model has seen and memorized during training. Therefore, perplexity can be used to detect whether a text was in a model's training data. This is useful for detect ing data contamination. If a model's perplexity on a benchmark's data is low, this benchmark was likely included in the model's training data, making the model's performance on this benchmark less trustworthy. This can also be used for deduplication of training data, e.g., add new data to the existing training dataset only if the perplexity of the new data is high. Perplexity is the highest for unpredictable texts, such as texts expressing unusual ideas, like "my dog teaches quantum physics in his free time," or gibberish, like "home cat go I." Therefore, perplexity can be used to detect abnormal texts. Perplexity and its related metrics help us understand the performance of the underlying ing language model, which is a proxy for understanding the model's performance on downstream tasks. The rest of the chapter discusses how to measure a model's performance on downstream tasks directly. 124, Chapter 3, Evaluation Methodology. How to use a language model to compute a text's perplexity. A model's perplexity with respect to a text measures how difficult it is for the model to predict that text. Given a language model X, and a sequence of tokens x1, x2, xn, xs, perplexity for this sequence is p, x1, x2, xn, 1n equals, 1p, x1, x2, a, xn, 1n equals, pi I equals 1n 1p, xi, x1, xi minus 1, 1n where p, xi, x1, xi minus 1, denotes the probability that x assigns to the token xi given the previous tokens x1, xi minus 1. To compute perplexity, you need access to the probabilities, or logprobs, the long-gauge model assigns to each next token. Unfortunately, not all commercial models expose their models' logprobs, as discussed in Chapter 2. Exact evaluation. When evaluating models' performance, it's important to differentiate between exact and subjective evaluation. Exact evaluation produces judgment without ambiguity. For example, if the answer to a multiple-choice question is A and you pick B, your answer is wrong. There's no ambiguity around that. On the other hand, essay grading is subjective. An essay's score depends on who grades the essay. The same person, if asked twice some time apart, can give the same essay different scores. Essay grading can become more exact with clear grading guidelines. As you'll see in the next SEC tie-in, AI as a judge is subjective. The evaluation result can change based on the judge model and the prompt. I'll cover two evaluation approaches that produce exact scores. functional correctness and similarity measurements against reference data. Note that this section focuses on evaluating open-ended responses, arbitrary text generation, as opposed to close-ended responses, such as classification. This is not because foundation models aren't being used for close-ended tasks. In fact, many foundation model systems have at least a classification component, typically for intent classification or scoring. This section focuses on open-ended evaluation because close-ended evaluation is already well understood. Exact evaluation 125. Functional correctness. Functional correctness evaluation means evaluating a system based on whether it performs the intended functionality. For example, if you ask a model to create a website, does the generated website meet your requirements? If you ask a model to make a reservation at a certain restaurant, does the model succeed? Functional correctness is the ultimate metric for evaluating the performance of any application, as it measures whether your application does what it's intended to do. However, functional correctness isn't always straightforward to measure, and its measurement can't be easily automated. Code generation is an example of a task where functional correctness measurement can be automated. Functional correctness in coding is sometimes execution accuracy. Say you ask the model to write a Python function, GCD, number1, number2, to find the greatest common denominator, GCD, of two numbers, number1 and number2. The generated code can then be input into a Python interpreter to check whether the code is valid and if it is, whether it outputs the correct result of a given pair, number1, number2. For example, given the pair, number1 equals 15, number2 equals 20, if the function GCD, 15, 20, doesn't return 5, the correct answer, you know that the function is wrong. Long before AI was used for writing code, automatically verifying code's functional correctness was standard practice in software engineering. Code is typically validated with unit tests where code is executed in different scenarios to ensure that it generates the expected outputs. Functional correctness evaluation is how coding platforms like LeetCode and HackerRank validate the submitted solutions. Popular benchmarks for evaluating AI's code generation capabilities, such as OpenAI's HumanEval and Google's MBPP, mostly basic Python problems dataset, use functional correctness as their metrics. Benchmarks for text-to-SQL, generating SQL queries from natural languages, like Spider, Yu et al., 2018, BirdSQL, Big Bench for large-scale database-grounded text-to-SQL evaluation, Li et al., 2023, and WikiSQL, Zhong, et al., 2017, also rely on functional correctness. A benchmark problem comes with a set of test cases. Each test case consists of a scenario the code should run and the expected output for that scenario. Here's an example of a problem and its test cases in HumanEval. Problem from typing import list def has _close_ elements, numbers, list, float, threshold, float, dash bool. Check if in given list of numbers, are any two numbers closer to each other than given threshold. Has _close_ elements, 1, 0, 2, 0, 3, 0, 0. 5, false has _close_ elements, 1, 0, 2, 8, 3, 0, 4, 0, 5, 0, 2, 0, 0. 3, true 126, Chapter 3, Evaluation Methodology. 11. The challenge is that while many complex tasks have measurable objectives, AI isn't quite good enough to perform complex tasks end-to-end, so AI might be used to do part of the solution. Sometimes, evaluating a part of a solution is harder than evaluating the end outcome. Imagine you want to evaluate someone's ability to play chess. It's easier to evaluate the end-game outcome, win/lose/draw, than to evaluate just one move. Test cases. Each assert statement represents a test case, def check, candidate assert candidate, 1, 0, 2, 0, 3, 9, 4, 0, 5, 0, 2, 2, 0, 3, true assert candidate, 1, 0, 2, 0, 3, 9, 4, 0, 5, 0, 2, 2, 0, 0, 5, false assert candidate, 1, 0, 2, 0, 5, 9, 4, 0, 5. 0, 0, 95, true assert candidate, 1, 0, 2, 0, 5, 9, 4, 0, 5, 0, 0, 8, false assert candidate, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 2, 0, 0, 1, true assert candidate, 1, 1, 2, 2, 3, 1, 4, 1, 5, 1, 1, 0, true assert candidate. 1, 1, 2, 2, 3, 1, 4, 1, 5, 1, 0. 5, false when evaluating a model. For each problem a number of code samples, denoted as K, are generated. A model solves a problem if any of the K code samples it generated pass all of that problem's test cases. The final score, called pass at K, is the fraction of the solved problems out of all problems. If there are 10 problems and a model solves 5 with K equals 3, then that model's pass at 3 score is 50%. The more code samples a model generates, the more chance the model has at solving each problem, hence the greater the final score. This means that an expectation, pass at 1 score should be lower than pass at 3, which, in turn, should be lower than pass at 10. Another category of tasks whose functional correctness can be automatically evaluated is game bots. If you create a bot to play Tetris, you can tell how good the bot is by the score it gets. Tasks with measurable objectives can typically be evaluated using functional correctness. For example, if you ask AI to schedule your workloads to optimize energy consumption, the AI's performance can be measured by how much energy it saves. 11 Similarity measurements against reference data. If the task you care about can't be automatically evaluated using functional correctness, one common approach is to evaluate AI's outputs against reference data. For example, if you ask a model to translate a sentence from French to English, you can evaluate the generated English translation against the correct English translation. Each example in the reference data follows the format: input, reference responses. An input can have multiple reference responses, such as multiple possible English translations of a French sentence. Reference responses are also called ground truths or canonical responses. Metrics that require references are reference-based, and metrics that don't are reference-free. Exact evaluation, 127. Since this evaluation approach requires reference data, it's bottlenecked by how much and how fast reference data can be generated. Reference data is generated typically by humans and increasingly by AIs. Using human-generated data as the reference means that we treat human performance as the gold standard, and AI's performance is measured against human performance. Human-generated data can be expensive and time-consuming to generate, leading many to use AI to generate reference data instead. AI-generated data might still need human reviews, but the labor needed to review it is much less than the labor needed to generate reference data from scratch. Generated responses that are more similar to the reference responses are considered better. There are 4 ways to measure the similarity between two open-ended texts. 1. Asking an evaluator to make the judgment whether two texts are the same. 2. Exact match, whether the generated response matches one of the reference responses exactly. 3. Lexical similarity, how similar the generated response looks to the reference responses. 4. Semantic similarity, how close the generated response is to the reference response. SES and meaning. Semantics, 2 responses can be compared by human evaluators or AI evaluators. AI evaluators are increasingly common and will be the focus of the next section. This section focuses on hand-designed metrics, exact match, lexical similarity, and semantic similarity. Scores by exact matching are binary, match or not, whereas the other 2 scores are on a sliding scale, such as between 0 and 1 or between -1 and 1. Despite the ease of use and flexibility of the AI as a judge approach, hand-designed similarity measurements are still widely used in the industry for their exact nature. 128, Chapter 3, Evaluation Methodology. This section discusses how you can use similarity measurements to evaluate the quality of a generated output. However, you can also use similarity measurements for many other use cases, including but not limited to the following. Retrieval and search: find items similar to a query. Rank items based on how similar they are to a query. Cluster items based on how similar they are to each other. Anomaly detection: detect items that are the least similar to the rest. Data deduplication: remove items that are too similar to other items. Techniques discussed in this section will come up again throughout the book. Exact match: it's considered an exact match if the generated response matches one of the reference responses exactly. Exact matching works for tasks that expect short, exact responses such as simple math problems, common knowledge queries, and trivia-style case tie-ins. Here are examples of inputs that have short, exact responses. What's 2 plus 3? Who was the first woman to win a Nobel Prize? What's my current account balance? Fill in the blank. Paris to France is like ____ to England. There are variations to matching that take into account formatting issues. One varia tie-in is to accept any output that contains the reference response as a match. Consider the question: what's 2 plus 3? The reference response is 5. This variation accepts all outputs that contain 5, including the answer is 5 and 2 plus 3 is 5. Exact evaluation: 129. However, this variation can sometimes lead to the wrong solution being accepted. Consider the question: what year was Anne Frank born? And Frank was born on June 12, 1929, so the correct response is 1929. If the model outputs September 12, 1929, the correct year is included in the output, but the output is factually wrong. Beyond simple tasks, exact match rarely works. Given the original French sentence, comment CAVA, there are multiple possible English translations, such as how are you, how is everything, and how are you doing? If the reference data contains only these three translations and a model generates how is it going, the model's response will be marked as wrong. The longer and more complex the original text, the more possible translations there are. It's impossible to create an exhaustive set of possible responses for an input. For complex tasks, lexical similarity and semantic similarity work better. Lexical similarity measures how much two texts overlap. You can do this by first breaking each text into smaller tokens. In its simplest form, lexical similarity can be measured by counting how many tokens two texts have in common. As an example, consider the reference response, my cats scare the mice, and two generated responses, my cats eat the mice. Cats and mice fight all the time. Assume that each token is a word. If you count overlapping of individual words only, response A contains 4 out of 5 words in the reference response, the similarity score is 80%, whereas response B contains only 3 out of 5, the similarity score is 60%. Response A is, therefore, considered more similar to the reference response. One way to measure lexical similarity is approximate string matching, known colloquially as fuzzy matching. It measures the similarity between two texts by counting how many edits it'd need to convert from one text to another, a number called edit distance. The usual 3 edit operations are 1. Deletion, br add-bad 2. Insertion, bad-bard 3. Substitution, bad-bed. Some fuzzy matchers also treat transposition, swapping 2 letters, e.g., ma-ts-ma-st, to be an edit. However, some fuzzy matchers treat each transposition as 2 edit operations, 1 deletion and 1 insertion. 130, Chapter 3, Evaluation Methodology. 12. You might also want to do some processing depending on whether you want cats and cat or will not and won't to be considered 2 separate tokens. For example, bad is 1 edit to bard and 3 edits to cache, so bad is considered more similar to bard than to cache. Another way to measure lexical similarity is n-gram similarity, measured based on the overlapping of sequences of tokens, n-grams, instead of single tokens. A 1-gram, unigram, is a token. A 2-gram, bigram, is a set of 2 tokens. My cats scare the mice consists of 4 bigrams, my cats scare the, and the mice. You measure what percentage of n-grams in reference responses is also in the generated response. 12 common metrics for lexical similarity are BLEU, Rouge, Meteor++, TER, and CIDR. They differ in exactly how the overlapping is calculated. Before Foundation models, BLEU, Rouge, and their relatives were common, especially for Translation tasks. Since the rise of Foundation models, fewer benchmarks use lexical similarity. Examples of benchmarks that use these metrics are Walmart, Cocoa Captions, and GEMV2. A drawback of this method is that it requires curating a comprehensive set of reference responses. A good response can get a low similarity score if the reference set doesn't contain any response that looks like it. On some benchmark examples, Adept found that its model Fuyu performed poorly not because the model's outputs were wrong, but because some correct answers were missing in the reference data. Figure 3.5 shows an example of an image captioning task in which Fuyu generated a correct caption but was given a low score. Not only that, but references can be wrong. For example, the organizers of the Walmart 2023 Metrics Shared Task, which focuses on examining evaluation metrics for machine translation, reported that they found many bad reference translations in their data. Low-quality reference data is one of the reasons that reference-free metrics were strong contenders for reference-based metrics in terms of correlation to human judgment. Freitag et al., 2023. Another drawback of this measurement is that higher lexical similarity scores don't always mean better responses. For example, on Human Eval, a code generation benchmark, OpenAI found that BLEU scores for incorrect and correct solutions were similar. This indicates that optimizing for BLEU scores isn't the same as optimizing for functional correctness. Chen et al., 2021. Exact evaluation 131. Figure 3.5. An example where Fuyu generated a correct option but was given a low score because of the limitation of reference captions. Semantic similarity. Lexical similarity measures whether two texts look similar, not whether they have the same meaning. Consider the two sentences "What's up" and "How are you?" Lexically, they are different, there's little overlapping in the words and letters they use. However, semantically, they are close. Conversely, similar-looking texts can mean very different things. "Let's eat, Grandma" and "Let's eat, Grandma" mean two completely different things. Semantic similarity aims to compute the similarity in semantics. This first requires transforming a text into a numerical representation, which is called an embedding. For example, the sentence "The cat sits on a mat" might be represented using an embedding that looks like this: 0, 11, 0, 02, 0, 54. Semantic similarity is, therefore, also called embedding similarity. 132, Chapter 3, Evaluation Methodology. Introduction to Embedding on page 134 discusses how embeddings work. For now, let's assume that you have a way to transform texts into embeddings. The similarity between two embeddings can be computed using metrics such as cosine similarity. Two embeddings that are exactly the same have a similarity score of 1. Two opposite embeddings have a similarity score of -1. I'm using text examples, but semantic similarity can be computed for embeddings of any data modality, including images and audio. Semantic similarity for text is sometimes called semantic textual similarity. While I put semantic similarity in the exact evaluation category, it can be considered subjective, as different embedding algorithms can produce different embeddings. However, given two embeddings, the similarity score between them is computed exactly. Mathematically, let A be an embedding of the generated response, and B be an embedding of a reference response. The cosine similarity between A and B is computed as frac AB, with AB being the dot product of A and B, A being the Euclidean norm, also known as L2 norm, of A. If A is 0, 11, 0, 02, 0, 54, A equals 0. 11 2 plus 0. 0 2 2 plus 0. 54 2 metrics for semantic textual similarity include BERT score. Embeddings are generated by BERT, and mover score. Embeddings are generated by a mixture of algorithms. Semantic textual similarity doesn't require a set of reference responses as comprehensive as lexical similarity does. However, the reliability of semantic similarity depends on the quality of the underlying embedding algorithm. Two texts with the same meaning can still have a low semantic similarity score if their embeddings are bad. Another drawback of this measurement